quiet little room. Thank you for coming. I appreciate it. By the way, these tutorials are supposed to help people with their research. So I will send out an appeal saying, like, what are the subjects you want to hear more about? And just write me back. Don't be shy. And if I hear things more than once, we'll definitely do them. And if I hear them once and I like them, we'll do them. And if I hear them once and I'm like, then I'm going to write you back and say, you're going to present Carlo. But no, seriously, send suggestions because I want this to work for people. And the people, the group of people we have changes every semester. So there's no reason not to go back. In fact, I'm going to refer right now to something I said at the beginning, which many of you were not here for, which is that this is like a memory. You're supposed to be remembering this, but of course you weren't here. And that is that frequentists, I'm getting used to this. This is a new iPad setup, so I'm going to stop for a while. Frequentists take derivatives. Because if you're a frequentist, you do things like find maximum likelihood. So you're like optimizing a likelihood or something. And Bayesians integrate. And in general, if you're doing an integral in your data analysis, you're probably a Bayesian. You're probably either a Bayesian or making a mistake. Sometimes both. And I spend a lot of time making fun of the Bayesians, actually. I'm known as a Bayesian, but I make a lot of fun of them. But today's thing will be entirely Bayesian. So we're basically going to assume you're a Bayesian in the room for today. I don't like assuming that because I'm trying to convince people to be less Bayesian. But if we want to meet people where they are, I think I should assume people are Bayesians. I think most astronomers are working in a Bayesian framework these days, which is a big difference from when I was a grad student.
It depends on my topic.
Right. Well, actually, my argument is it depends. It should depend on your goals. Okay. But you're absolutely right that in astrophysics, it depends on topic. Because if you're measuring stellar abundances, you're a frequentist. Yeah. If you're like mapping the dark matter in the Milky Way, you're a Bayesian. Good, great, love that. Okay, so I just want to say, so what is MCMC? So Markov chain Monte Carlo is a workhorse. And actually a lot of people say, oh, I'm doing an MCMC. I'm doing this project where I'm detecting planets using MCMC or whatever. Like if you have MCMC in the title of your project, that's like saying I'm doing my project with linear algebra because it's just a tool and it does exactly one thing, which is it does integrals. MCMC just does integrals. People often don't think of it that way. Here's the way I think people are often using MCMC. People are often using MCMC and they like corner plots. Remember, everyone loves corner plots. And part of the problem is that Foreman Mackey and I made the corner plot at the same time as we made our MCMC sampler, where you have like some parameter A and some parameter B, and you have like some posterior in A, some posterior in B, and now I'm gonna have a very bad time drawing the joint. I just gave myself a hard job. But anyway, there's some like, where these are histograms, like these are histograms of A and B, and this is like a joint, this one here is like a joint 2D probability distribution. And people, you've done some sampling and here you're plotting like the histogram of your samples. What does that have to do with doing an integral? Like you're like, I just got the samples, what does that have to do with doing an integral? What it is that these two ways to think about it. One is this 1D probability of A given your data is the integral of the probability of A comma B given your data, dB. So this 1D integral you've drawn is an integral. This 1D distribution is an integral of a two-dimensional function. So you used MCMC to do that integral. You just thought you were plotting the samples, but by plotting the samples, you were doing that integral. There's another sense in which it's an integral, which is that even if you look at a pixel, remember this is like some image of your 2D posterior, what's the density you put in that pixel? It's the integral of a probability over that little pixel. So the number of samples that fell in the pixel is like the integral of a probability distribution over that pixel. So in both cases, you're integrating. It doesn't look like you're integrating here, but you are. Good. So let me, everyone agree with that? Everyone believe me? Anyway, you are doing integrals. Whenever you're doing MCMC sampling, you are doing integrals. And here's the integral you're doing. You're always doing something like some integral of some function of your parameters times the probability of your parameters. And I'm going to drop the given y. Like I should write given y here, but we're going to get notationally ugly in a second. So I'm just going to drop that. Just wait, zero on me. D theta. This thing here is your posterior. This is your posterior. This is your parameters. And this is some function of your parameters that you're integrating, which could be like the function that is 1 inside this pixel and 0 outside this pixel. That was the integral you were doing there. That function q of theta is 1 if you're inside the pixel and 0 out. But you might be doing much more interesting integrals. You might be, this q might be how much money you make if the parameters are this value. And then you're computing the expected amount of money you're going to make. Which, by the way, is what terra hunting is going to need to do, because we make a lot more money if we find a planet in the habitable zone than if we don't. And so we're going to open up that habitable zone, and then we're going to do an integral, and our most important planets will be the ones that deliver the most cash. And it always makes scientists uncomfortable when they think about cash, but guess what? We have to fund projects. And if we are successful with terra hunting, there will be a terra hunting too. And if not, there won't be. If you don't know what terra hunting is, it's irrelevant right now. But I refer to terra hunting a lot in these data analysis things because it's my big data analysis thinking these days. Okay, when you're doing MCMC sampling, what you're doing is you're taking this integral. By the way, I've never used this iPad before, so all hell my way. Taking this integral, and you are approximating it as a sum over samples of Q. I've already made a mistake. Sorry. And I want to write it in black anyway because it's important. Whoa, what the hell just happened? Is there like an undo?
There's an undo. Oh, right.
Did I touch it? You're treating it as 1 over n times the sum from I equals 1 to n of Q of theta n, theta I mean. And I should put a little like wiggly thing because it's an approximation. So the point of the sampling, these are your samples here. I guess I should go back to red. These are samples. So in every case you're using MCMC, you don't always notice this when you're doing MC, but every time you're using MC, this is what you're doing. You're finding a set of samples that are somehow drawn from P of theta such that this sum is a good approximation to this integral. Everyone good? By the way, that's the definition of a sampling. This statement, if you want to say my sampling is good, like, we argue about this all the time. By the way, the big problem with MCMC, which I won't get a chance to do in real detail, but actually we could do a separate thing on. By the way, if people want, I'd be happy to do another week where we're like, how do you know your MCMC sampling is good? Because often it's not good. But if your MCMC sampling is good, it means that for every quantity that you care about, this approximation is a good approximation. So if you need to know how much money you make to within 10%, you're asking for this to be 10%, with like a 10%, have an error or an uncertainty of 10%-ish on it. And notice how subjective this is. Some people have very simple functions they want to do here, like they're just making these plots. Those are very simple functions. You're just asking for the number of samples that appear in certain bins. These are very easy integrals. Some people are doing very hard integrals. Like if you're exponentiating some tail, like imagine what you care about is like the probability. Imagine we have a planet in terra hunting that is not that close to the habitable zone, and we're just asking what's the probability it's in the habitable zone. And somebody does this and say, oh, the probability that it's in the habitable zone is 10 to the minus 4. We have probably not computed that integral very well. Like that's a very hard integral to compute, like tail probabilities, whatever. So, how good your sampling is depends on what your goals are. So it's subjective. It's another point of subjectivity. One of the themes of this, there's two themes of these sessions. One is this theme, and another theme is subjectivity. So I'll just write that explicitly. This is the definition. It's the definition of a good sample. I'm sorry that my handwriting is so bad.
Sorry, can I clarify?
Yeah, go ahead.
Just in my mind, it's always been that we integrate to approximate the posterior.
Yes.
And what we show in the corner plot is just some, I don't know, like some range of the posterior, or just, like quantile or something. I think I'm a little confused of when you combine integration and what we see in the corner plot. And
so the argument I was trying to make here, but I was not making very well, is that when you make these plots, you are in fact doing integrals. So think about this plot, right? What is this? This is a histogram in bins, right? This is a bin histogram. The number of samples in one of these bins is technically an integral over the probability distribution. So even doing this, you've done an integral.
Okay.
So even this plot is an integral. It's an integral in two senses, actually. One way it's an integral is that when you plot this plot for B, you've integrated out A. And second is, even making this plot, you're doing counts in bins, and counts in bins are approximations to the fraction of the probability that's in the bin, which can be written in this form. Then this Q function would be an indicator function, which would be like, are you in the bin?
Okay.
So it's a little bit technical. You're very right to say, like, that's not an integral. You're just plotting the samples. But it is an integral, technically, whenever you do a histogram, you're doing an integral of some kind. And actually, Foreman, Mackey, and I have this whole like theory that histograms are functions, and you should think of them as functions that are generated by integrals and whatever. We have all this, we have a whole theory of it, which we've never written down. Because, astronomers love histograms. So, really, I should do a session on the histogram, because the histogram is such an interesting object. And we use it a lot. And there's a lot of things you can do with histograms that are like slightly wrong, which, when you're dividing histograms and stuff, like things can go badly wrong. Okay, good. Imagine you're in like, so imagine you have just been given, you like have a homework assignment, which is you need to integrate Q of theta, P of theta, D theta. What are your options? I just want to make a comment here, which is that MCMC is almost your worst option to do this integral. For instance, if you can do it analytically or like in closed form, do it in closed form. You should definitely do that first. And you might think, oh, that's never possible, complicated data analysis. But actually, if your problem is like Gaussian priors with Gaussian likelihood function, sometimes you can just do this integral. There's a weird paper by me and Adrian and Boris Leisted that's archive only that shows that a bunch of the integrals that come up in Gaussian, linear Gaussian, like if you have Gaussian priors and linear models and Gaussian errors, so a bunch of the integrals are just analytic. So that's one question, one idea. So one idea is like just do the integral like analytically. And then the next thing is if theta is low dimensional. If it's low dimensional, like if theta is like 1 dimensional or 2 dimensional or 3-ish dimensional, it's getting scary at 4. But if it's like 1, 2, or 3 dimensional, you should use like a quadrature or something. You should just use an integration technique. So you should use something like I don't actually know much about the integration techniques. I should know more about them. But you just look up like numerical integration techniques and use one. And and if it's very high D, like very high dimensional, like thousands of dimensions, or even hundreds to millions. Actually, in machine learning methods, you can easily get 10 to the 12, right? Like if you do a deep CNN, you can easily have 10 to the 12 weights. The answer is give up. You will not do that integral. You will never do it. And people often fool themselves into thinking they've done integrals that they haven't done. Actually, I should say that one comment I should make on this is that actually in this case, there's a bunch of papers in astronomy where people have done integrals that are millions of dimensions. For instance, in the CMB, like the CMB, part of the CMB is censored, right? Because the galaxy's in the way. And people have done MCMC in which they done samplings of the obscured part of the CMB. Those samplings are in a Gaussian case where you can actually do the sampling exactly. So that's a place where it actually works. And then there's other cases where people have lots of parameters where they do the MCMC and try to integrate, and they just recognize in the paper there's no way this sampling is converged, but our view is it's better to do some samples than none. So there might be, it's an interesting question, which I haven't figured out in the philosophy of science of like, should you use techniques that aren't working? Because they still might be more conservative than techniques would work, you know what I mean? Anyway, I don't know. It's an interesting question. Nobody really knows the answer to those questions. They're like really open questions, like how do we use methods wrongly? Because if you have a million free parameters, you literally can't do the integral. There's no
David?
human. Yeah. Go ahead, Will. That's Will.
No, that's me, the voice in the ceiling. What you're saying is technically true, but I think you're overly pessimistic because the cues in your language that you're interested in are almost always like super low D summaries of those 10 to the 12 dimensions. And in that case, even though you can't actually, think about just doing like spin flips in the Ising model or whatever. As soon as you have any number of spins, the space is so combinatorially huge, you never explore all of them. But the magnetization is a really low summary.
But you might only need to know like the temperature at which like things start to change state or whatever, and then you can do that. You're right. Yeah, absolutely.
Exactly.
So right. So but notice that in those cases, you're going to have to appeal to heuristics to decide that you're okay. Like it's hard to know that you're okay. You know what I mean?
That's right.
I'm agreeing with Will, and that's why I kind of agree. There's some papers. There are these crazy, like one example of extremely Bayesian data analysis that's happened recently is a bunch of people have inferred the three-dimensional structure of the dust in the Milky Way by doing lines of sight and then reconstructing the full three-dimensional where all the dust is. And those things are incredibly highly parameterized models. And most of the people working on it are true Bayesians. And so they do try to marginalize out all their free parameters. And in those cases, I think in no case are the marginalization integrals correct, because they're just too high dimensional. However, the people who do them argue, and I think maybe correctly, that it's still more conservative to do a incomplete marginalization with a bad MCMC than no marginalization whatsoever. I don't know. It's an interesting question. So I think there's a lot of question marks there, and many people are in this state. Many problems have thousands to millions of parameters. Actually, so we have some advice. So I'm going to switch to advice, and then we'll talk about MCMC. Just a little bit of advice. One piece of advice is if you are in like 3 to 12 parameters, the code that Foreman Mackey and I wrote called MC shines in this region. It doesn't require tuning. It's very easy to use. Yada, yada, yada. And there's lots of other methods. There's nested sampling, there's parallel tempering, there's lots of other things you could do. So like MC and all the other sort of basic methods. If you are in the sort of I'm going to leave a gap because there's a sort of judgment zone. But if you're like 15 to 1,000, people have shown some success with Hamiltonian. And it depends a little bit on how bad your problem is. But Hamiltonian, we recommend, once you go well above 12, we generally recommend that people go Hamiltonian. Unless your problem has some beautiful structure, like lots of your direct dimensions are exactly Gaussian or something. And if lots of your directions are exactly Gaussian, usually you want to make some hybrid thing. So like if you have a lot of problem structure, it's a good time to talk to somebody who's like a hero of MCMC and have them help you like refactor your problem. So for instance, Adrian and I have a problem called the Yoker, where we find all of the binary star systems in the apogee data or any spectroscopic data. We find the RV, the binaries in the radial velocity and data, and we use like a hybrid thing that does some part of the integral analytically and the part of it that isn't analytic with a sampling technique. And we do that because we have to do it on so many stars. We don't have time to do full MCMC on everything.
Can I ask?
Yeah.
Why Hamiltonian? I'm just
like, why does it work?
Hamiltonian hater.
Good.
So I need to know why Hamiltonian is.
I don't know. I don't have a good intuition. Hamiltonian, by the way, Hamiltonian methods are methods that are very, they turn the problem into a like dynamics problem. Actually, all MCMC problems are dynamics problems, oddly. The original MCMC algorithm, the Metropolis-Hastings algorithm, which we're about to write on the board, was created to simulate, I think, like neutrons in a nuclear reactor or something. It was originally done to do a dynamics problem in physics. And Hamiltonian is just the generalization of that to include momentum. So in Hamiltonian, you give all the particles not just positions in the space, but momenta in the space, and then you turn on a Hamiltonian and you evolve them dynamically. You need to have derivatives. So this thing has additional requirements. You need derivatives, meaning like you need to have written your code in like JAX or PyTorch or something that gives you derivatives with respect to your parameters. And then the samples kind of fly around your posterior as if it's a Hamiltonian like dynamical problem. I don't know why that works better. I literally have no intuition. Yes.
Could I add some intuition, or is it going to take us too far afield?
Yeah. No, it doesn't take us too far afield.
So, because of these weird situations and high dimensions where all the volume is at the edges, generically, every high dimensional posterior concentrates in a thin spherical shell centered on but not including the peak of the posterior.
Yes.
And so because that shell is so much thinner than it is across, you're trying to basically wander on the surface of a sphere. And it is much nicer to have a memory of where you are going. And that is exactly what momentum gives you. You like bounce around on the infinitesimally thin surface dimension, but flow coherently along the surface due to the momentum. And so it lets you go all the way around to the antipodal point of the sphere in one sampling step, rather than having to take random walks whose size is the thickness of the sphere. And it's exactly what you wrote there. It's just the cursed dimensionality. Great.
I that intuition could easily be correct. I try not to have intuitions in high dimensions, but Will said something that's extremely important, almost that we could do a whole hour on it, which is that when you're in very high dimensions, you're never near the peak. Like, so if you have thousands of parameters, like the maximum likelihood point in thousands of parameters will not generically be near any of your samples. Because if your sample is sort of 1-ish sigma this way and 1-ish sigma this way and 1-ish sigma that 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 way for 1,000 different dimensions, it is the square root of 1,000 sigma away from that point. So generic points in your posterior will be 30 sigma away from your maximum likelihood point. And so your intuitions break down. When we plot these kinds of plots, your intuitions are pretty good. Like there's a blobby thing and there's probability at those blobs, but in the very high dimensions, it doesn't look like that.
Can I ask the ceiling a follow-up question?
The ceiling. You're the ceiling, Will.
Hit me.
Well, but practically, we have like a little bit more than 15 parameters, and Hamiltonian Monte Carlo never worked because the parameters were very correlated with each other.
Yeah, well, when it works really well in high dimensions. But like what Hogg mentioned, right? Hogg said you need derivatives. That means it needs to know a lot more about the structure of your problem, and the structure of your problem needs to be a lot more gentle in order to make it go. Yeah, everything is super problem dependent. This is not the MC situation where you just hack something up and throw it at your Hamiltonian Monte Carlo and it's done. This is pain.
For sure. Juliana.
Like so back in the old days before we were using MC and we were just using like Markov or like, you know, some sort of thing that got you down to. One of the strategies we used to do was just do like grid sampling across the parameter space to like get you to make sure that you weren't going to get stuck somewhere, that like you would actually initiate in lots of different places. Is that a strategy that like is relevant in these days with these tools? Because like it was effective back then.
Absolutely.
And there will be a dimensionality that breaks it where you can't even like.
Yeah. So we you know, as I opened by saying, just before you walked in, I opened by saying that that we could do a whole semester on MCMC. And one of the big problems with MCMC and all methods that are adaptive like this is you can get trapped. You know, you have your posterior has multiple peaks, you can get trapped in a peak. And you can pass all of your MCMC tests, but you've actually only sampled one of the peaks because your MCMC thinks that's the posterior when there's another peak over here. And the only way you can find it is brute force. In fact, it's proven that the only way you can find it is brute force. That's the no free lunch theorems. In optimization, there are these no free lunch theorems that say that you have no choice but brute force. So yes, when you really want to make sure that you have the right answer, you have to do many restarts, either randomly or on a grid or something to check.
I mean, I have seen like people who posted little videos of their samplers sampling where like there are some things that are not like traditional MCMC where, you know, it's effectively throwing out like, it's always sending out like a ranger, right? Like you settled your town, but it's always sending things. Like I've seen things where they like, I don't know if was it cases like flow MC, like some of them seem like they're a little more robust to that, or I mean, actually, tell us your feelings.
Yeah, good. So everything's very problem specific, and there's lots of like tweaks of MCMC. As we're about to see, the conditions of a correct MCMC are actually very weak. So you have a ton of choice when you build an MCMC method. The conditions are extremely weak about what you do. You do have to obey the conditions. And you know, the MC code which we maintain, we get lots of pull requests where people modify it and pull and then give us a pull request. And we reject almost all of them because almost all of them do violate one of the conditions. But once you obey the conditions, you're good. And that means you have tons of opportunity to do weird things. Like, for instance, there are methods that try very hard to make big moves. There's also methods that do kind of annealing type things where they try to see the whole parameter space without data and slowly grow the importance of the data so that the samples fall into the data. And so, which is like nested sampling and annealing methods look like that.
So nested sampling is that? I've never known what that is. Like,
nested sampling is quite hard to explain. Yeah, nested sampling is quite hard to explain, and the people who use it tend to be 100% true believers. So it's hard to get any. But yes, it is. What it does is it basically reduces the importance of the likelihood in some stages, and so you're sampling the whole prior, and in other stages, it's only sampling very high likelihood parts of the data. So it's sort of or of the parameter space. It like.
Got it. So that sounds useful.
Yes, and there's trade-offs in MCMC methods between kind of robustness, simplicity, and speed. Like simplicity, speed, and robustness are all to some extent in conflict here. And like, and so MC is designed to be like simple and fast, but then it's not particularly robust. And nested sampling is very robust, but it's slow and complicated.
I have a question actually. So
Yeah.
imagine you have all these parameters, right? But sometimes you know the parameters cannot have infinite like values, right? You have like some
Yes.
constraint.
Yes.
That should in principle help you, right?
Yes.
A parameter that can be a number around 2, you know, and you know more or less it's between 2 and 3.
Okay,
you
good.
Don't need like
good. Let's
a
say
huge sample, right?
Good,
you have
good.
like an idea.
So, right. Well, first of all, we're going to be Bayesian here. So we're going to write down a problem and we're going to solve it. And when we write down the problem, of course, we're going to put priors on our parameters. So because we're Bayesian. So that, first of all, you're first saying your priors should represent your beliefs. But you might also be saying another thing, which is that you want to be working in a parameter set where it's easy to describe your beliefs. So often you can transform your parameters into different forms, and sometimes you get into a situation where you might have a parameter that can go from 0 to infinity, but there's an equally good parameterization where it goes from 0 to 1. And it's much better to work in the situation where it goes from 0 to 1 for exactly kind of the reason you're implying. You know what I mean?
Yeah.
Okay, good. Let me just say what the problem set up. There's many reasons that MCMC is a bad idea. Actually, I was gonna write here, if you go from if you have 1 to 4 dimensions, as I said up above, you should really look at whether or not you could just do a quadrature. Or other just direct methods for integrating, or grid the space and explicitly just integrate. By the way, one of the things that Farmanaki and I were going to do is make a reading list of papers that used MC in one-dimensional problems. It's really not a good idea. In far fewer compute steps, you could do your integral. If you have one dimension, don't use MCMC. Just fucking plot it. Anyway, so the setup, here's the setup. The usual setup is I have data, Y, I have parameters, beta, I have a likelihood, which is like the probability of the data given the parameters. And sometimes I also say and your beliefs about your model. I was being really careful in the beginning of this class, but I'm just gonna be not at all careful now. And you have a prior. You have to have a prior on your parameters. Oops. You have to have a prior on your parameters because in order to use MCMC, you have to be Bayesian. Because we're going to do integrals in the parameter space. If you're a frequentist, this thing doesn't exist. If you're a frequentist, this thing doesn't exist, and then you can't do integrals. By the way, one thing I guess I should have, I said something a long time ago, and I'm just going to repeat it. This P of theta has the property that it is greater than or equal to 0 for all values of theta. And it integrates to 1. It integrates P of theta, d theta is 1. I'm just saying that because in a second, things aren't going to integrate to 1. So I just want to remind you. This, by the way, those two conditions, if you are like me, if your math level of sophistication is like mine, that's the definition of a probability distribution. It's greater than or equal to 0 everywhere, and it integrates to 1. There may be other conditions. I think the space theta is weird. I think there might be other conditions, but I don't want to think about it. The likelihood has the property that the integral of P of y given theta dy is 1. And it has the property that P of y given theta d theta is not something you would ever want to do. Like bad. And so another like just comment is that you can't integrate a likelihood function, at least not over the parameters. You can only integrate it over the data. And this is fundamentally the difference between the frequentists and the Bayesians. The frequentists operate on this likelihood, which you can't integrate. So you take derivatives of it. Bayesians can multiply by prior, then they can do integrals. And there's lots of ways to think about this. And I go off about this forever. And I think I talked about this on the very first class, which is that this object has units of 1 over data. That's why when you integrate it with respect to data, you get 1. This object has units of 1 over parameters. That's why when you integrate it with parameters, you get 1. This is per unit parameters or something. So I always think about units. By the way, the statisticians never think about units. And I wrote a little note about like probability distributions and how you manipulate them. And the statisticians are like such a physicist. They literally, even though they recognize that you can derive a lot of statistics from units, they're like, that's irrelevant. Anyway, I don't know. Okay, good. So the setup is, so now remember in Bayesian inference, so, and I get to say one of my rants about Bayesian inference. So in Bayesian inference, what you do is you take your likelihood and you multiply it by your prior, and this updates your prior beliefs to your posterior beliefs, right? And so the posterior beliefs, so this equals your probability for your parameters given your data. This is your posterior. And this is your prior. And this is your likelihood. But there's a horrible thing out front, which is you have to renormalize. And people often write that Z as like the probability of the data. And I have extremely strong philosophical reactions to that. So I just call it Z. It's just a normalization factor. But you have to renormalize because you see how this expression over here has the wrong units. See, this is units per parameters. This is units per parameters. This is units per data. So this side has units of per data per parameters. We have to divide by something that has units of per data to get this to the right units. And the reason I'm emphasizing this is this thing is quite hard to know. Like, to get this, you have to integrate. You have to do a big integral to get this. But we're doing MC so that we can do integrals. You see, we need, like, we can't do the integral because we don't have an integrating. Anyway, so the MC was invented because of this problem. MCMC was invented because of this problem. It's easy to write down, usually not always, but in many problems we have, it's easy to write down this likelihood function. In many of the problems we have, it's easy to write down this prior. It's easy to construct this probability and unbelievably difficult to get this factor Z. That is the typical situation. Almost all data analysis, I do have that problem. So the point of MC, or of MCMC methods in general, is that you only get this product. It is not correctly normalized. Yeah.
Like, is that normalization, the normalization factor has no dependencies on the data of the parameters?
It does depend on the data, it turns out, but not the parameters. It's a weird object.
It reflects.
Yeah, go ahead, Will.
It reflects the probability density of the data you actually got under the predictions of your prior.
Yes, it's the thing that Bayesians call the evidence. But in my lab, this Z is called the FML, which of course stands for fully marginalized likelihood.
It's a very appropriate name. I should catch on.
Yeah, that's why we use it. It's the fully marginalized likelihood. It is the thing you would get if you could integrate the left side over theta, which you just can't do. Well, sometimes you can do. Actually, sometimes you can do it. And then if you know it, you can actually use better methods than MCMC. But MCMC is assuming that you have this object. So what you have is you don't actually, the crazy thing about MCMC is you're trying to do integral or get a sampling of this function, but you don't actually quite have this function. What you have is this product, which is related to that function by a constant you don't know. And that, by the way, once you see this problem structure, that strongly recommends that you should either be working with the log of P of theta given Y. Like gives you that feeling, right? Because you don't want to care about some overall, and then that overall factor just becomes some offset. So, or you want to be working with ratios, P of theta 1 given Y over P of theta 2 given Y. And actually almost all methods in this area either work, well, the most things that are called MCMC work with this thing, but then there's a set of methods that are based on diffusion or based on like physical diffusion processes that work on the gradient of the log of the probability. And so there's a whole set of methods called like Langevin dynamics, I think. It's got some name like diffusion, Langevin dynamics, something like that, that uses the gradient of the log probability. And if you read the machine learning literature, which is usually painful, this thing here is called the score.
Oh, is this like the score-based diffusion?
Score-based methods, score-based diffusion. Actually,
it's terrible terminology. It's awful.
Don't start with me.
Yeah.
It's not my fault. I would never have called that the score. You know what that should be called? It should be called the force. Because if you think of the log probability looks like an energy, and gradients of energies are forces. So in Hamiltonian dynamics, in Hamiltonian Monte Carlo, that is the force. It's terrible, but Laurence Levasseur, our favorite person, is an expert at these methods that use the score. And it's been unbelievably successful in machine learning. There's a whole bunch of methods called diffusion. Maybe you've even used these tools, stable diffusion, where you can make crazy pictures. Those are based on that.
Why has that been more successful than other methods? Do you know? Like, what's the like what do you gain by going to this space?
The reason it's been, I believe, I'm going to make it up right now, but I believe the reason it's been successful in machine learning is that when you have very large amounts of data, you can see gradients in the log density. And so it's possible to like train a predictor of the density of the data, of the log of the density of the data. And they're all kind of based on that somehow. Because of course in machine learning methods, there aren't really parameters,
right,
there's just data.
Right, but like why is that winning?
It has something to do with the fact that it's easier somehow to locally ask in which direction do I need to go to get more data than it is to take the ratio of two densities. This is like, the method we're gonna write down right now uses a ratio of two densities.
But like point locations.
Right, you have to choose some location, you have to decide on some scale.
Two samples to estimate a gradient versus taking a.
Whereas in the score-based method, you can be somewhere in the space and you look around and like you go like, which direction do I need to go to get to more data? And it's kind of obvious somehow. I don't have much intuition, but somehow it's related to that. By the way, Laurence Levasseur has some recorded lectures on the internet that are so beautiful about diffusion. And that are, say again? Yes, I'll put it in the notes. Let me just write for Levasseur. That's her name, and she has things about diffusion. And there's various talks that are on YouTube. They're amazing because the thing that's great about Laurence is she came to machine learning from physics. So she talks about machine learning like a physicist. But anyway, by the way, I'm just saying all this because there's things that might be better than MCMC that we're not using yet. Because all this work has gone into score-based models and nobody has really figured out how to use it for just normal data analysis problems. Well, some people have actually, but I haven't. I certainly haven't, and I don't know what the current state of play is. Good. Okay, good. So here's the problem. So the problem statement is, I have a function, the input is a function f of theta, which is equal to p of theta, given it's equal to your posterior times some unknown constant. I guess it's z times it. And I don't know z. And I want, that's the input, and the output is a set of samples theta 1, theta 2, theta 3, theta n. That's the problem statement. And I want the samples to be good. I want the samples to be good samples in the sense that I wrote at the beginning, which is that for every integral I care about, q of theta, p of theta, d theta, I want this sampling approximation to that integral to be a good approximation. That's the goal. I'm just going to write the Metropolis-Hastings algorithm down because it's so beautiful. And by the way, if you have a low-dimensional problem, if your problem is on the lower end of this 3 to 12, you should just write your own Metropolis-Hastings algorithm. It's like 4 lines of code, and it often just solves your problem. And then not only do you get your problem solved, you feel an immense amount of pride that you didn't start by typing pip install to solve your problem. So, and you learn something by it. And then you have a little workhorse that you can then build up and do new things with it, play around with it stuff. So I actually strongly recommend that people implement Metropolis-Hastings. Foreman Mackey and I have a paper called like using MCMC, a data analysis recipe. I'll also send that around. I'll send that and Laurence Levasseur talk around. And in that paper, we say, the first thing we say is, you should build your own MCMC before you install anybody else's, because you learn so much by doing it. This is the basic algorithm. Whoa. Here's the basic algorithm. It's called Metropolis-Hastings. Yeah. I apologize that my handwriting is so bad. I'm going to get better at using this. This is a new device. Metropolis-Hastings. MCMC. By the way, this is a typical thing where it's named after the wrong people. Like something like 4 people were involved in making this, and 2 of them get named. I don't know. It's the usual mess. Metropolis is a person, not a word.
Really? That's a cool name.
You know that the Outer Bridge crossing is named after a person named Outerbridge? That's not why it's called. That's why it's not called Outer Bridge Bridge.
Yes.
I love this. I want to collect names of things that are named. Anyway, whatever. The Metropolis-Hastings algorithm is outrageously simple. So here's the idea. The idea is, let's feed like a little bit of symbolic here. So there's some space theta. Here's your theta space. This is your parameter space. And what you want to do is you want to get samples in the theta space. Theta space, of course, is not 2-dimensional. It's got many dimensions, but let's think of it as 2-dimensional just because then we can visualize things. You have some point, your first sample. Don't ask me how you got your first sample. It has to have finite probability, it turns out. But other than that, we don't care quite how you got your first sample. What you're going to do is you're going to put down a probability distribution around your first sample, and you're going to select a candidate sample. So this first sample, I'm going to call sample I, because actually it's not your first sample. We're in the middle of doing this operation. You put down a candidate sample. We're going to call this candidate sample star. So meaning, and you draw it from a distribution that's centered on your previous sample. So you have a sample, you're going to choose a new one. Why are you centering on your current sample? Because this method is adaptive and it knows you've already got a sample. So it wants to try other places that are near your sample. Then what you're going to do is you're going to ask about the probability ratio. You're going to ask about the probability of theta star given data divided by the probability of theta I given data. And if this is greater than 1, you're going to accept it. So you're going to set theta I plus 1 equal to theta star. And if this is less than 1, you're going to use this as a probability, and you're going to accept it or reject it with a probability based on this ratio. Yeah.
Is the area defined by theta?
Say again.
Is the area around the first?
You mean, how do I choose this probability
Yeah.
distribution? I'll say a word about it. It's easiest to write down the Metropolis-Hastings algorithm if you don't do anything adaptive at all. You just up front chose a probability distribution and you just always use the same probability distribution. You're thinking like, shouldn't I be more adaptive than that? You're like, that's dumb. I should be more adaptive than that. We will say words about that in just a second. This is the dumbest version of Metropolis-Hastings. So in the dumbest version of Metropolis-Hastings, through some work, which we usually call tuning, you figured out how to set that probability distribution, and then you put away all your tuning and you start going, right? So you've chosen this probability distribution somehow. So this, by the way, this probability distribution that you have here is like the probability with which you choose theta star, given that you previously had theta I. So this and this thing is called, this thing has a name, this thing is called the proposal distribution. And it can be anything, but we usually choose a Gaussian or something like that. And I'll say a word about that in a second. So let me just add a little bit of notation here because I want to be very clear about what we're doing. This ratio we're going to call R, and if R is greater than 1, we accept it. If R is less than 1, with probability R, I should say capital P probability, with probability R, we accept it. And with probability 1 minus R, we reject the sample. And when you reject it, here's the weird thing. When you reject it, you copy your last sample. You don't throw it away. You don't throw away this choice. You copy the previous sample. So theta I plus 1 equals theta I. That's the Metropolis-Hastings. And then there's a million things to say about this. One thing to say about it is, obviously, this produces correlated samples. Why are they correlated? There's 2 reasons they're correlated. One is every sample is drawn from a distribution near the previous sample. So nearby samples will be close to each other. But there's another reason they're correlated is sometimes you literally repeat the same sample and you feel like an idiot, but it is the correct thing to do. Remember, you want a fair sampling. I didn't say the sampling was interesting. I said it was fair. And so it'll be an ugly sampling. So your samples are very correlated. And this leads to a whole question of like, what's the autocorrelation time? Like how far down the sampling chain do I have to go before I have a truly new independent sample? And it turns out this is a very hard thing to estimate. Another thing to say is what Sabina brought up, which is that you probably want your proposal distribution to be adaptive. And if you make it adaptive in the sense that you make it arbitrarily vary as you go, it slightly modifies the algorithm. Because if you make it adaptive as you go, there's the probability of jumping one direction isn't the same as the probability of jumping back. And then you have to add an additional factor here. There's a Q over Q factor out here, which is like your probability of jumping one way versus the probability of jumping back, which complexifies the statement of the problem. So it's easier to do in the non-adaptive form. If you don't make the probability proposal distribution adaptive, there's a tuning step where you have to like run MCMC with different sizes and shapes for this distribution, with this proposal distribution, until you get one that works well. And by the way, the main reason that MC, I guess there's two reasons. There's two reasons, this is an advertisement for MC. There's two reasons that MC has been successful as a product. One is it's incredibly easy to use, but the other is it doesn't require tuning. It self-adapts in the way that you kind of want it to without complexifying the algorithm. So MC is a good thing because it doesn't require tuning, but almost all algorithms require tuning. And one of the reasons why you hate Hamiltonian is outrageously hard to tune because you have a proposal distribution and you have a mass matrix. So it's a bad, Hamiltonian problems are very hard to tune. And there's a very useful concept in MCMC, which is, and we're running out of time, but there's a very useful concept in MCMC, which is acceptance rate. So look at this algorithm. In this algorithm, sometimes when the probability is greater than 1 or very close to 1, we will tend to accept the sample. If this ratio is very much less than 1, we will probably reject the sample. So imagine you're accepting samples all the time. You're like, cool, we're always accepting samples. This MCMC method's working so well. It's like, no, if you're accepting all the time, it means you're not moving very far. Because as you're jumping around in the space, you're never getting a ratio that's very far from 1, which means you haven't moved very far in the likelihood or the prior sense. So you neither want your acceptance ratio, you don't want your acceptance ratio near 1 or your acceptance rate near 1 because it means you're just not moving very far. If your acceptance rate, however, goes to 0, then your samples are all exactly the same sample and you never go anywhere. And that means you're jumping too far because you're jumping to places where this ratio is tiny. So the best acceptance rates, there's a whole literature on what the best acceptance rates are. It's literally a huge literature about this, but it's about a third. A quarter. There are papers that are as low as a quarter and papers that are as high as a half. But that's one of the ways we tune MCMC methods. We generally tune them until the acceptance rates are a quarter, a half. Yeah.
So I go to the third floor a lot.
Yes.
Learn about things.
Yes, they care deeply about this on the third floor. In fact, I think Andrew Gelman is on sabbatical here, and Andrew Gelman has written multiple papers about this.
But they also deeply, so that's why I started thinking about it.
Yeah.
They deeply care about acceptance rate, but they also deeply care about estimated sample size.
Good. Estimated sample size. Good. Very good. Good. Yes. Let me just, we're essentially out of time, but let me just say this. So what is the idea behind this autocorrelation time? You've taken n samples, but remember I said the samples are very correlated. They're correlated with some length scale in your sampling. That length scale is like T, you could call it T auto, the autocorrelation time, meaning how many samples do I need to go through before I have a truly independent sample? And the true sample size is actually n over T auto. So sometimes you can make 150,000 samples, but then you find out that your autocorrelation time is 30,000 and you have 5 samples. Even though you ran your computer all night, you actually only have 5 samples. And you might think, oh, 30,000, that sounds crazy. Oh, no. We've done MCMCs where the autocorrelation time is longer than 1 million. In fact, usually it gets to the point where you can't measure it. They're very hard to measure these autocorrelation times. And so actually, when you want to ask, how well have I sampled my problem? One of the critical things is this ratio, the number of samples you have divided by the autocorrelation time. But the autocorrelation time is very hard to measure, so you won't have it, you won't know very accurately how many samples you have. And even that doesn't quite answer your true question. Remember, your true question is, how well did I approximate the integral that I care about? Wait, wrong way. The integral, how well did I approximate that? That's really what you care about. So what you really care about is something like the variance on the estimate of your integral. And that will be a dimensionless number times this. So this, remember in Poisson things, your variance goes like your number of measurements. So the variance on your integral will be proportional to this, but times a prefactor, which depends on how ugly your integral is. So that they're right that this is the thing you want to maximize. And so one of the reasons why, so in MCMC methods, a super interesting thing about MCMC methods, by the way, Metropolis Hastings is just one of the first one of a million methods, which people were shouting out earlier. We are willing to spend a lot of computation to reduce the autocorrelation time. Because if an MCMC method takes 4 times longer but has 1/10 the autocorrelation time, you've just won. And that's why one of the reasons we love Hamiltonian. It's also a reason people love nested, because nested comes out and comes back in and gives you an independent sample. Nested samples, you can, there's a, and we do even dumb, like in the Joker, we have concordance sampling that actually has an autocorrelation time of 1. But it's outrageously expensive. It's like incredibly expensive, but we get an autocorrelation time of 1. Anyway, good, we're done. Maybe we should talk more about MCMC since this is just an intro. Thank you for coming, people.